Welcome to the Physics Discovery.
Today we are going to talk about the skydiving.
We separate its whole motion into two parts.
The first part is the skydiver jumps from the plane and experiences a free-fall motion.
In part 1, after the skydiver jumps from the plane, the skydiver is accelerating downward to the ground, which is due to the gravity. At the same time, the air resistance exerts on him and gives him a force upward. According to the equation, F equal to the 1/2 c rho s v squared, which c is a constant drag coefficient since the whole motion is always between the skydiver and the air. Rho is the air density, s is the surface area, v is the velocity. As the skydiver is falling down, the air density increases, the surface area stays the same, and the velocity increases due to the gravity, so that means the air resistance also increases as the skydiver falls down. The skydiver will eventually reach a terminal speed, and this is the speed at which the drag from air resistance exactly balances the force of gravity pulling him down. After the skydiver releases the parachute, since the air resistance increases instantaneously, therefore it gives the skydiver a larger upward force compared to the force of gravity, and can drag the skydiver going upward for a while. In this video, the skydiver uses the square parachute. However, different shapes of parachutes have different advantages.
The oldest parachute design appears in an anonymous manuscript from 1470s Renaissance Italy, and it is a conical-shaped parachute. Conical parachutes were designed to save people from short falls rather than from falling out of airplanes. Conical parachutes get the most air resistance by trapping air drastically, and could not be used for skydiving.
Circular parachutes can expand rapidly into a bubble, so that circular parachutes have a great advantages for slowing or even stopping as quickly as possible. Some circular parachutes can be destroyed since they were falling too quickly and stop so fast, which is why it has many other deceleration devices to slow the open rate of the parachute.
Square parachutes cannot slow the falling as quickly as circular parachutes. However, square parachutes are more stable, since airflow is only temporarily redirected and not trapped.
After the parachute is completely released,
according to the general gas equation, PV equal to nRT, so that we can get P equal nRT over V, where P is the pressure, N is the amount of gas, R is the gas constant, T is the temperature, and V is the volume. Also, according to the geography, we know that for every single 100 decreases in altitude, the temperature increases 0.6 degrees. Therefore, as the skydiver falls down with the parachute, the temperature keeps increases, the volume trapped by the parachute stays the same. The amount of gas does change, but only a little, so it can be neglected, and the R is constant. Therefore, the pressure inside the parachute also increases while the skydiver falls down. During this motion, the pressure inside the parachute is larger than the pressure outside, so that the parachute gives the skydiver an upward force and slows the velocity more. Finally, the skydiver will reach a terminal speed again, which is safe enough for the skydiver land on the ground.